Okay. I hope everyone can hear. It's George Hathaway here, way up in Toronto, or near Toronto. I'm an experimentalist, so most of the activity around here is things and devices and knobs and switches and stuff. The meat of what I'd like to talk about happens to dwell on those kinds of things rather than equations and things that are neatly able to be put on a screen. So what I'm proposing to do is discuss briefly what was required in this recent calibration effort for Jim's calibrator. But before that, I'd like to discuss briefly, to continue from the pick up from what Lance was talking about. And Lance, as you've just heard, has come up with a testable theory. And I was asked to determine whether it would be possible to put together an experiment where the charge on a particular object could be made rather large, just to make sure that the previous experiments, which I'll describe momentarily, were not seeing a subtle effect that that was predicted by Lance, but perhaps the coupling coefficient was different as he described. So the previous set of experiments, there have been quite a few with regard to looking at the weight change of a charged body. And he mentioned Martin, I believe he mentioned Martin Timar and myself. And the thing to realize with Lance's discovery is that the force is supposed to be in the vertical direction, not sideways. For instance, if you think, well, gee, I remember a guy named Brown, wasn't his name Brown? And he did an experiment where he had very high charges on a dielectric material, and he looked at them on a pendulum perhaps, and he looked at them moving on a torsion balance. We had done this experiment as well several decades ago, back to and up to about 30 kV in oil, and taking all the precautions, as many as we could, with regard to removing artifact, and saw no evidence of force in the Biefeld-Brown, which was, of course, essentially going this way. I don't recall them ever testing it in the vertical dimension. However, recently, Martin Timar and group in Dresden have made a rather exhaustive examination of the Neobfeld experiments with various geometries and various kinds of devices charged to, I think 20 kV was his top charge voltage. And he did a really good job of trying to isolate these high voltage systems from artifacts and from influences that could cause spurious readings. And he came to the conclusion that no, there was no relationship between the charge on a body and an associated gravitation or force. And he looked at all sorts of, as many orientations as you can think of, with his devices, including vertical. So he came to the conclusion that, gee, doesn't look like there's the kind of result that Lance had been predicting. Lance's predictions are really, I agree with his description of Kaluza kilotons, because he was predicting forces in this direction on charged bodies where the charges, for instance, resulting from voltages in the kilovolt range, would be in the pounds of thrust, you might say, easily measurable by the most unsophisticated kinds of experimental apparatus. Well, Lance asked me to examine situations where the charges are on objects would be much greater than what Martin had been working with, just in case for some reason there might have been a threshold or a nonlinearity that might indicate that there would be a something magical would happen. Kilotons would appear once you got over, I don't know, maybe 50 kV or something like that, or 43 kV, whatever it was. So he asked me to consider a higher voltage experiment, which we were able to do, or which we were able to put together anyway. It's still in the process. And so what we've done, and if I can show people, if they're interested, some of the material and the apparatus that we've put together to carry out this experiment. And the primary source of charge, well, there are two primary sources of charge. One is a Glassman 150 kV DC both polarity test, where we are charging we're going to be charging two spheres or spheroids. One is about 18 inches in diameter, and the other is a meter in diameter. And I can show you those if you wish. I can walk out to the lab. That's why I've got this other computer, and I don't have the one that has the Woodward report. However, so the Glassman would get us to 150, will get us to 150 kV, both polarities. And I also have two Van de Graaff machines that were made a long time ago for looking at the Podkletnov gravity beam experiment, if anyone remembers that, where we did not find the kinds of results that Podkletnov had claimed. These are two high voltage devices, electrostatic machines that are calculated or theoretically able to produce probably close to 900 kV each, but practically, because they're not perfectly spheroidal, they're not operating in a vacuum, they have little imperfections on the surface, etc. They can climb to probably 500–600 kV. And I have two of them. One of them is positive and the other is negative. So with those pieces of apparatus, I started to consider that we could do the kinds of tests that Lance is interested in, up to a couple hundred kV. And so that's all very nice, but one of the concerns is that the electrostatic machines, which are Van de Graaff machines, have produced very high voltages, but at microamps of current. So how do you make sure that you are measuring the voltage and thus the charge on these machines when you have such a low current? Typically, a device that can calibrate a high voltage machine, such as in high voltage engineering, in power systems, uses a particular kind of voltage divider that has a fairly robust front end in terms of its impedance or resistance in case of a DC machine. In the case of the Van de Graaff machine, the problem is this low current. So I had to make a special voltage divider for the Van de Graaff machines that was a very high impedance front end, so that I would not drain the very tiny currents produced by the Van de Graaff machine and still have an accurate reading of voltage. So that has been put together. The final aspect is how to measure these forces that, according to Lance, are rather going to be rather large, but in my estimation from the work I've done in the past, likely to be very small. So we had to design have designed a load cell that is capable of for instance, looking at about 0.04% of weight change. But the other thing to realize is that when we're dealing with 200-300 kilovolts in any kind of laboratory setting, everything gets charged, and that includes the measuring apparatus, like the load cells. So we have to take special precautions to isolate the load cell and make sure that the electrostatic charge that builds up on all these surfaces does not screw up the readings. Those are just a couple of the issues that need to be addressed. The others are the humidity of the room, and which will bleed off charge, and concerns about how the charge might sneak up the support structures. So if you wish, I can walk out to the lab and show you the size and scale of some of these things, if that would be useful. Hal, is that acceptable in this case?
I think that will work, yes.
We would love to see that.
I can stop the share.
Yeah, you can stop the share, and I'll take this computer.
I'll use speaker view, everyone, and then you'll see George in big.
Yeah, okay. So I'm heading out into the lab now, and we'll show just the scale of some of the things that are required to do the kinds of tests that Lance is hoping for with regard to charges resulting from voltages up to 200-300 kV. So here we are in the back, the high bay, and above me you can see the 1 meter diameter sphere. By the way, the ceiling is 16 feet above the floor. That is a polished aluminum sphere of 1 meter diameter. It is used typically along with this sphere, which is 75 centimeters in diameter, to measure high voltages using calibrated arc discharge length between the two. In fact, we're not using it for that purpose. We will be using the suspended sphere as one of the charged objects in Lance's experiment. The other shape is part of a Van de Graaff machine you a little that is going to be suspended as well from a protected device up there on the ceiling, which is the, I don't know if you can see it, but there's the force gauge. So the force gauge will have a cord that drops down and suspends these two shapes. Okay, how do you charge them? Well, they're going to be charged from, as I say, a Glassman, which is a commercial device up to 150 kV, but above that, up to 300 kV or so, are these twin Van de Graaff machines. You can see how tall they are, which were used in the Podkletnov experiment some time ago. One is positive, one is negative, and they will be attached to the suspended masses or weights by a flexible conductor, so that the weight can be measured by the force gauge or the load cell way up there. But how do you measure the charge on these Van de Graaff spheres accurately? It's really difficult since they're such small current devices. Well, I had to construct a special voltage divider, which is this one, for the purpose, and it's oil filled and has a series of very high value half gigohm resistors, and that will be the voltage divider with which we will measure the voltage on these Van de Graaff machines, as well as calibrate or the Glassman. So done so far is made sure that we can measure the weight, the dead weight of these masses, the one that's hanging from the ceiling, as well as the smaller one, and we can charge them up to a particular voltage. We've been able to go up to just about 200 kV to make sure that everything is calibrated. And so we will be forging ahead with the experiment at the appropriate time, I guess. You know, Lance can describe what the appropriate time is, which will be, I hope soon. So that is a brief walkthrough of the high voltage end of the lab, which I hope will give you an idea of the kind of scales that we're working with. And I can stop now and take any questions with regard to the experimental procedure, if you wish.
George, a question on your lab facilities. What's the square footage? Your Toronto?
11,000 square feet.
Wow. Okay. Thank you very much. It's large.
So we can see, so I can center this thing that I'm about to show.
There, I'll just open that.
Okay. So, hey, can you hear us? So one of the things that we were interested in about Podkletnov stuff, and maybe you can answer, he's got a picture here of a basic impulse generator. This is a 2 megavolt Marx bank. So when Podkletnov's experiments were being ran, they used quite a bit of discharge energy into that superconductor, and it was a layered superconductor as well, which was quite important. There's a boundary between those two layers. But we were wondering, have you tested it with very high impulse currents, other than just the static charge stored between two spheres, for example?
No, we didn't, because Podkletnov has had claimed that he got similar results with Van de Graaff machines, and it just required the charge.
See, that is quite a claim. Have you heard of Power? Is that how you say it? Power with his pulsed discharge superconductor experiments in a small vat?
Yes, maybe Chantel or Amy are going to discuss that. If we want to do that, maybe we should do that offline, or on a general discussion, because those are experiments I can certainly discuss, but I think in the interest of time, it might be useful to continue with the general theme here.
Thanks. Yeah, we'll have a chance to chat about that. I'll let you get back to it. Thanks. And by the way, fantastic laboratory, quite amazing.
This is Amy. I'll interject. I've got some funny stories about Power and those Podlet-Knopf style discs, and I won't do a tangent here, but I can talk about them later if you want. NASA Marshall Space Flight Center, my dad, Richard Eskridge, there did some pretty extensive collaboration with Power back in, I don't know, it was like 2014. And they got some really interesting results. And we have some videos of the equipment like basically exploding with like the impulse that was coming off of those discs. It was pretty cool. But we can discuss that further later.
Okay. Are there any further questions with regard to Lance's experiment?
Georgia, just let me thank you for that summary and the walkthrough. That really looked great. And I'm glad you emphasized the vertical nature. And I would just say that I looked at the Townsend Brown stuff a lot and tried to find indication. And the big thing was everything was horizontal that they were testing. And so I thought maybe if we just rotate to the vertical, it's all going to open up. That was part of the reasoning. But I appreciate you summarizing that, George, and showing us your lab and, proving that you're definitely the man to do this. So thank you.
Hey, Lance and George, can you hear me? Yeah, so really cool. And, I do comms in the other part of my job, and I'm hoping that you have the time to flesh out that wave equation a little bit, because I'm really curious to see what would happen in the sort of the non-steady state case, because I think there might be some interesting stuff there, maybe relating to that Podlet-Knopf stuff as well.
Okay. By the way, with regard to, I'll just interject, go the opposite what I'm saying. I wrote a paper on the Podlet-Knopf spinning disk experiment in Physica C back in 1999 or something like that. So if anyone's interested in first tier, I consider experimental examination of Podlet-Knopf spinning disk experiment, I can send you the reference. So now back to Jim and Hal.
By the way, I do have your report, George. It's just that I can't open it for some reason. My stupid computer refuses to open the Word doc. I wonder if Jim has it. Maybe they could open it and share the screen with us.
Yeah, if you can, that'd be great. Otherwise, I'll be walking through it anyway in the same way that I have through the lab.
Sorry, Hal, I do not have George's final report. I just have his preliminary.
I'll send it to you, Paul, because I can't open it. This stupid machine won't do it. It's the school system. They've got some weird 360 word thing going on. It's ancient. It won't open the new stuff. I'll just mail it to you, Paul.
Okay, and I'll be yakking away here and arm waving and pointing out stuff. And during that time, it might actually materialize. So now we go from the large scale down to the very small scale, and we're now in the process, or I'm going to describe measuring forces in the micronewton range, and this was as a result of Jose Radal, who I think is on this, somewhere down there, re-examining the basis on which Hal and Jim were using their calibrator, which you saw in detail, in some detail anyway, in their presentation. And this was the 3-coil arrangement. In fact, I can show you a vertical version of the 3-coil device. I don't know whether it's possible to see, but right there, is that visible? There are three coils. In this case, they're mounted in a vertical direction. So what was the requirement? It appeared that there was a discrepancy between Jose's calculations and what was being assumed by Hal and Jim as a calibration factor. This led to some concern that perhaps it would be beneficial to have an independent check on the calibration. So I was asked to put our apparatus to work, and we have balances that are down to the 10, well, a couple of balances down to 10 micrograms, 3 of them actually, and then an ultra micro balance as well, that yellow thing that just appeared on the screen and then disappeared. So the reason that I had these balances, Sartorius and Mettler and things which I'll show you in a bit, was because I had put together one of the 3, I guess, prominent test balances to look at Jim's ideas. And here's a picture of the vacuum balance that I built that has all the balance guts in a vacuum chamber. I don't know how much of that you can see because I don't see the screen, but there's a complicated bunch of stuff in there. And I claim that with that apparatus, I'm able to look at sub-micronewton thrusts in a horizontal direction. Well, in order to calibrate that balance, I needed calibrated balances, which unfortunately happen to work in the vertical direction. There are a couple of Sartorius balances to 10 micrograms, or actually 20, operational, and I'll show you another one which is down to that range too. So I figured that with those devices, I could maybe make a contribution to ensuring that that Jose's calculations, which are based, or his recalculations based on Babbage et al., which Hal presented earlier, the paper of, were reasonable. And I could not find any publications that showed an experimental proof of Babbage's calculations. So which was unfortunate because those calculations seem to be applicable to a reasonably wide range of magnetic systems, of magnetic force systems. So I suggested that maybe I could put together a test to confirm or deny the validity of the Babbage equations. And that picture I just showed you of those Jim's 3 coil arrangement was hanging under one of the balances, and I wrote a report on the results of that, the summary of which Hal put up those curves that you saw, and at the beginning of Hal's report this morning, I say this, I guess this morning, it was early afternoon my time, showed a reasonably close correspondence between the results that we got down to the microgram range and the calculations of Babbage. So that was happy making. But it also showed that there was this discrepancy, which Hal had mentioned, of a factor of 4 or so that needed to be accommodated in future reports of the thrusts from Jim's thrust stand. In addition, Martin Timar had been doing experiments with some of Jim's, or a device of Jim's, and had claimed that the thrusts that he was seeing from Jim's device were much smaller than what Jim was claiming. And so there also was a question about, well, is his calibration okay? Is Martin's calibration acceptable? So it was also determined that I would, or suggested, and I agreed, that I would examine Martin's calibration procedure. And his calibrator is this, and I will endeavor to, I hope everyone's not getting too dizzy, me moving around here, but Martin's calibrator is a commercial device from a company called Moticont, and it consists of a air core coil of wire. You can see the scale here we're looking at, and a little cup that has a magnet in it, a permanent magnet. And this, the coil fits into this very small annular space between the magnet and the cup. So there was a question about, well, gee, maybe Martin's device, or his test, you know, he was scraping against the side with this coil, or maybe there was something else going on that threw his calibration off. And so I was asked to put together an experimental procedure where I was able to fix the exact position of this coil right in the center of that annular space. But as you can imagine that if you just suspended this from the bottom of a balance, you know, it'd be moving around like this, and it might bang up against the sides of this thing and cause, as it did, some spurious results. So I devised a method whereby it was possible to completely fix a vertical or virtually vertical movement of this coil in that space. And I did it by remembering that there's a whole history of microengineering, you might say, based on called pin and cup pivot bearings. So take a tiny bit, a little chunk of sapphire, for instance, laser drill a little V shape in it, and then put a hardened steel or other material pin in it, and you've got a wonderful pivoting capability. For instance, as used in, remember these things? These are called moving coil meters for you youngsters. And you can see the wonderful, this is a spring-loaded device, but boy, is it a wonderful piece of engineering. What's inside there is something called the D'Arsonval meter movement, which is a coil wrapped around a piece of high permeability material in a magnetic field. And it looks somewhat like this, if I can show you two of these devices. Let me see. So here is the guts of one of those meter movements. Here's a second one, just happen to be side by side. But they are so delicate that hardly any force is required to move them, and in a constrained motion. So what that meant was that I could mount one of the coils of Martin's device on the end of one of these D'Arsonval movements. Here it is sitting here, and since the movement is very slight, I can get a virtually linear movement up and down of the coil, but the coil stays exactly in position because it's fixed by the movement of the meter movement. So that is one of the ways that I was able to ensure that the multi-cont coil was able to be fixed within that cup, and I did the measurements, and at some point we can, if we get that report up, I sent a report to Jim.
I've got the report,
and,
I can share the screen with you.
Okay, but before, actually, well, if people are interested, maybe we can go into that afterwards. I did want to make one point, though, that it really is unfortunate, isn't it, that gravity works this way. It would be great, since we're using force balances, thrust balances that happen to like to work this way, that we could have some kind of gravitating body or something way over here, or we could tilt our whole thrust balance 90 degrees and use gravity as that wonderful constant, well, relatively, depending on how much Lance is going to tell us later, to be a constant force in a particular direction. We can't. So wouldn't it be nice if we were able to hang calibrated weights that have force directions this way, but translate into force directions this way? Well, here's a possibility. These damn things are so sensitive, these meter movements, and I've done it just with this movement today. I can make this thing move with, what was it, 3 micronewtons of force. So if I put 3 micronewtons down on this side, I can move this top, these are balsa wood pieces, 3 micronewtons that way, you might say. So one of my thoughts is that perhaps I will try to install this thing, not with all this stuff, in my balance and add very small weights to this side and see whether I get a good calibration factor on my on that balance I just showed you. Anyway, it was sort of a new possibility. Just to also to give you some idea of the forces that we're dealing with when Jim says, you know, 10 micronewtons or 5 micronewtons, or in our case, you know, a couple of 100 nanonewtons. You know, what does that mean in terms of objects that we have? Well, one of the calibrators that or the calibration weights that I've had to use in calibration comes from Mettler, and it is a calibration weight that is 0.05, I don't know if you can see this, 0.05 milligrams. That's 50 micrograms. And I got to be very careful opening it, because if I blow on it, it could disappear. And what I mean by that is it is a piece of aluminum, a couple of microns, an aluminum wire, a couple of microns in diameter, and about half a centimeter long, bent into a V shape. And I don't think you'll be able to see it, but it hangs on it has to hang on a particular piece of a hanger in this cup. It's really hard to see in there, and it is electrostatically charged. So you got to handle it with tongs and be very, very gentle with it. It's the smallest calibration weight you can buy, but with it at 50 micrograms, I can calibrate our various systems here to ensure that when I say there's a particular calibration standard, I can trace it back to a standard. So that kind of gives you maybe a visual representation, even though I had to do it with fingers and stuff, of the kind of forces that we're dealing with. Just a little breath and away goes your calibration weight, and $400 goes down the drain. So anyway, with that, I will close it up. I think I'm just about...
Oh, you've got another 15 minutes or 10 minutes if you want me to bring up the report now, so I have it ready to go.
Okay, well, perhaps it might be instructive for folk to take a look at that. If you want to bring it up, I will exit the lab. Yeah, in this report, what I tried to do, thank you very much for bringing this up, was to ensure that the kinds of tests that I was being asked to do, I could justify, and that I could take account of the kinds of spurious artifactual forces that plague these kinds of measurements. At the large scale, the forces are of electrostatics and image charges and all sorts of other stuff are large, but so are the expected forces. In this case, in the case of this particular experiment that you're looking at now, the forces are really small, and so other precautions have to be taken. For instance, in this picture, you see a Mettler 10 microgram balance, which has a hang down. Oop, there it is. And underneath it, it's mounted on a granite machinist table for anti-seismic concerns. There is a shield, which is, you can barely see around the actual test apparatus, the test which is going on underneath. So that tends to minimize air currents, which will definitely mess up the measurements. And in the case of Jim's calibration coils, the coils have to be positioned exactly in case they are being compared to the Babbage equations. Exactly, the movable coil, which is the middle one, has to be positioned exactly halfway between the outer ones. So I have put together a translation, a micro stage, a couple of stages from an optical experiment, so that we can move those coils into exact position that is representative of what Babbage equations are meant to to show. There's an example of the stage. In addition, we need to get power or current to the middle coil, which is the movable coil. So how does one do that without going into the case of using, let's say, gallium or some other liquid metal? Even if we did use liquid metal at these small currents that I'm trying to get down to, the liquid metal would mess up. It has its own forces. There's adhesion. There's tensile force. There's all sorts of different forces that would mess things up. So I found that using very small diameter wire, I could find a sweet spot or a sweet position of the wire that leads from the lab frame to that middle coil with number 44 wire, still be able to produce the kind of current, or allow the kind of current to flow that would give me micrograms, micronewtons of force, and not overheat the wire too much. So that is sort of an overview of a couple of concerns. Also, you can see in this particular picture, Babbage assumed, of course, theoretically, that the three coils were completely concentric. And in order to do that, that's why the stage in the back moves horizontally as well as vertically. I could position the coils so that they, according to that angle you see, sitting there, are as close to perfectly coaxial as possible. So that was part of the setup for recalibrating Jim's calibrator based on the Babbage equations. If you scroll down a little bit more, we'll get to Martin's. So there's Martin's coil, which I showed just a moment ago. He suspended it in one case from a beam, which you can just see across the top, and he suspended the coil, and the cup holding the magnet is on the pan of one of the balances. This is one of the ways I calibrated it. But of course, since this is a magnetic system, I have to be careful of stray magnetic fields messing up the balance. So there's a plate of mu metal underneath. You can see that square plate. And there's a draft shield and a whole bunch of other stuff, which is in the report. If you go down a little bit more, let's see if there's that picture of the little, I think it's down further. Well, that's the final result. Let's see. I guess it's the picture's up a little farther. It's a picture of, or a photo of the ability, you might say, of these D'Arsonval, you just, I think, passed it, D'Arsonval meter movements to keep just keep going down the coil in exactly the right position in the Dresden situation. So anyway, I guess it's flying by here. The net result is that I was able to confirm that Martin's Dresden calibration was good, and I was able to confirm that the Babbage equations were applicable to actual physical apparatus and measurement, which leads me to believe that at least Martin has a correct calibration when he measures thrusts on one of his balances, and that Hal and Jim can rely on the Babbage, the Babbage equations to calibrate their calibrator. So, and I don't know whether that report is universally available, but I have to leave that up to Mike and NIAC to determine. Anyway, that is about all for me.
Well, that brings us up to the 5-minute mark, so that was pretty much perfect. Thanks, George. Are there any questions for George? I can stop sharing the screen.
Yes, George. I'm Mark from Falcon Space. Have you read this paper by Doyle Buehler?
And it's called
Oh, you can't see it, can you? It's
Exploratory,
called
yep.
Exploratory Research on the Phenomena of the Motion, or excuse me, of the Movement of High Voltage Capacitors. So there it is again.
Yes, I believe I have.
In there, it actually states that the experiment did not work while it was in a Faraday cage with the parallel plate capacitors. Have you tried? Is your building made out of a metal?
The building is partly concrete. It's mostly concrete walls, and it has a steel roof.
So if the steel roof is grounded, you might be inside of a Faraday cage, and it wouldn't. You wouldn't expect any effects, according to this paper.
That may be the case. I have my doubts, but when I did the original experiment on the Townsend Brown experiment, it was parallel plates in oil.
Right.
So,
We've both tried this experiment independently.
Yeah, extensively. We've actually got a research group that also has tried this experiment 3 other times to replicate it, and none of us have received any results except for one who used very thin wires, which we are certain were leaking a very large amount of ionic current.
yeah, I haven't ever found any positive results, you might say, from a Biefeld-Brown effect.
Same here. We've tested over 7 different configurations and never received anything from any of them.
We did find a lot of ways to make mistakes and think you're getting something, though.
I betcha.
The false positives and the calibration problems become a real issue when measuring around electrostatics, just because the field geometries will create anomalous forces that have to be accounted for.
That's right.
Yeah,
All right, well, thank you very much.
all of these effects tend to have a lot of noise that you have to control for. And there's also usually very specific configurations that you need that are not exactly obvious, that you're not necessarily going to stumble upon, and specific factors that have to be happening, like with the rotating superconductor disk thing for Podletkinov, he only saw his effect during deceleration through a specific range of RPM.
Okay.
So there's always weird little things like that you have to get just right, or you're not going to see anything.
Is that Amy?
Yes, I'm sorry, this is Amy.
Joe Blood, that's what it says on the screen.
That's my pseudonym
Oh,
for my
okay.
computer.
All
All my
right.
devices have different pseudonyms. Hold on, let me see if I can put my name in here. Yeah, my name's not Joe.
I didn't think so.
You might be, those who are interested in the problems of force measurements, at very small force measurements, may be interested in a presentation I gave at the Tennessee Valley Interstellar Workshop a number of years ago, where I highlighted, and I did the same, essentially same presentation at the Estes Park workshop. It's last year or 2 years ago, I guess, highlighting a great number of potential pitfalls that you can stumble into when measuring small forces. So that might be of benefit if you ask Hal for that, a reference to that paper of mine in the proceedings.
It's on the SSI website. You can download it for free. It was 2016. So it's a Estes Park Conference Proceedings 2016 on the ssi.org website. So any further questions? No? Well, thank you very much, George. That was very instructive. I really enjoyed the tour around your lab. It's amazing.
Thank you.
We can now break for lunch, and we'll be back at 1:30, and Jim will kick off again and tell you about all the very recent stuff with the the Mega Drive and the recent sliders and that sort of thing.